So thank you for joining this morning from wherever you're joining us from across the world. Just as notification, this meeting is being recorded, the plenary session, I should say. And so if you do not consent to your recording, I guess we would ask that you please do not speak or put anything into the chat. We're going to be using this workshop to inform a workshop report as part of the IEA Bioenergy Task. Other housekeeping items, and I'll go through this in the agenda. Please keep yourself on mute, and if you do have a comment or question, we're going to be holding most of those for the breakout sessions that we have. But please use the raise hand feature so that as best we can keep this in an orderly fashion. So without further ado, I'm going to go ahead and get started. I'm just going to talk briefly about our agenda for today, and then I'll kick it over to my colleague, Fionnuala Murphy, who's going to talk a little bit more about what we are trying to accomplish today. Okay, so a little bit about IEA Bioenergy Task 36. IEA Bioenergy is a conglomerate of multiple tasks focused on various biogenic and waste streams. This particular task is entitled Material Energy Valorization of Waste in a Circular Economy. We have 5 task areas that this group works on. And largely this comes down to information sharing and best practice sharing across the member countries. And this particular workshop, as you're going to hear from Fionnuala briefly, is focused on our sustainability task and really recognizing that the priorities of sustainability do vary significantly between regions of the world and even within particular countries themselves. Certainly here in the United States, there's a diversity of different sustainability priorities when it comes to handling these waste streams.
Hello.
And I'm going to go ahead and again remind everyone to please mute if you are not one of the speakers. Thank you. So we have 8 countries representing 4 continents in this task. I see several of my colleagues on the call today, so it's good to see them. And again, when we're talking about waste here, we're talking about a variety of different waste streams. This can be fractions of municipal solid waste, such as paper waste or textiles. This can be biosolids from wastewater processing, fats, oils, and greases, and plastics waste. So we're going to be talking about a lot of those today. And again, thank you for joining. So our agenda for today, after Fionnuala gives a brief introduction on the workshop and our objectives, we're going to have a series of talks from several groups in the United States here. And we're all kind of focused on the 3 different pillars of sustainability. So we'll have a talk about economic sustainability drivers, environmental sustainability, and social sustainability and siting. And each of those will lead into a subsequent breakout discussion. We also have put together a Google survey, and we'll put the link to that Google survey in the chat momentarily. We are using this to kind of standardize responses between this workshop and other workshops that we're hosting as part of this task. So last December, we had a workshop hosted in South Africa. And, again, the results from this survey are going to be compared to that. And then we will also do one in the fall focused on Europe. So please, if you're attending, please take the time to answer those Google survey questions. There's only 6, so they should be pretty quick. It's just kind of ranking different sustainability indicators that you see as critical. So I'm going to go ahead and kick it over now to Fionnuala, who's going to talk a little bit about what we're trying to accomplish today. So thank you.
Perfect. Thanks, Bo. I'll go ahead and share my screen here. Okay, hope everybody can see that there. Yeah, so my name is Philila Murphy. I'm an assistant professor in the School of Biosystems and Food Engineering in UCD, and I'm a task member. So my area of expertise is in sustainability assessment. And as Bo has already mentioned, one of the tasks we're carrying out within the overall work program is to identify what sustainability indicators are important to different stakeholders and in different regions. So as Bo mentioned, we carried out a workshop in Durban in South Africa. We have our US workshop here today, and we're carrying out a workshop in Europe in October as well. So that allows us to identify or bring together different stakeholders in different regions to identify what sustainability indicators they find important. So I'm going to just give an overview of some of the sustainability assessment methods we use, and I'll introduce the survey as well. Okay. So as I'm sure you're all very aware, there's a variety of different waste treatment strategies and technologies which have been applied to treat a range of different wastes, be them biological waste, be them material wastes, be it general municipal solid waste as well. Within the task, what we are doing is looking at the different waste management strategies to see what the environmental, economic, and social impacts of those different strategies in different regional contexts are. We're doing this because when we're looking at methods to treat waste, we see over time with varying different regional policies that we're moving more towards a circular economy. So we're trying to recover as much resources and energy from waste materials as possible. So when you look at the approaches to waste management over time, they have moved from your traditional approaches from landfill to new approaches such as waste to energy. So in some regions that's very well established. In some other regions, Ireland, for example, we have fewer waste energy plants than in other regions. So we're interested in seeing what the pros and cons of these different approaches are. So if we're talking about waste to energy, it does have benefits in terms of you're reducing the volume of the waste that you need to deal with. You get energy recovery as well. So you have in combined heat and power generation, we have electricity generation and also heat that we can recover. But there's also then environmental emissions which can occur. So emissions to air, and we also have dioxins and heavy metals being produced from incineration too. So then there's new technologies, pyrolysis and gasification, which are also alternatives. So particularly treating particular types of waste. But what we want to determine is what those environmental impacts are. And if they were to be implemented on a large scale, what are those impacts, both environmental, economic, and social? So that's the, I suppose, recognition we've come to in the task, that when we're looking at novel technologies, there's obviously the technical and economic performance, but we also need to look at the environmental aspects. And we do that by using life cycle assessment. So some of you may be aware, there's international standards which govern life cycle assessment. So essentially what we do is we look at the full life cycle of a product from production to use to end of life treatment. So that's our waste management treatment. Essentially, we look at the inputs and outputs of the system, and then we can relate those to environmental impacts. So when we consider sustainability assessment of waste management systems, in the academic literature, it's really been the environmental impacts which have been mainly studied, with the economic and social impacts lacking. But when we're considering waste management systems that we need to develop to make our waste management system more circular, we need to look at the environmental, economic, and social impacts together. So I'll briefly just have a look at these different the different methods used to estimate these impacts. So as I mentioned in environmental impact assessment, we mainly use the life cycle assessment tool. So that allows us then to essentially what we need to. What we do there is we develop an inventory with the elementary flows. So we essentially have a result where we have all of we can identify and quantify all of our emissions from a system, so to air, to soil, and to water. We can relate those to midpoint impact categories. So those are the ones we typically see in the academic literature and in reporting around waste management systems. So climate change or global warming potential, we look at acidification potential, eutrophication potential, those sort of midpoint impact assessment methods. And then we can go to the end point. So becoming more uncertain, but we can draw a relation between our midpoint impacts and our endpoint. So we can relate the impacts to impacts on human health, impacts on the natural environment, and impacts on natural resources. Looking at the literature, this is from a review from 2021, which reviewed the LCA studies of waste management systems. So you can see these are the different environmental impact categories that were considered in life cycle assessment. So the vast majority of studies looked at global warming. So 95 studies considered global warming potential. And the other main ones considered were acidification, human toxicity, and terrestrial eutrophication. So there's a range of different impact categories that we can consider in our assessment of waste management systems, but they're not all always applied. So the main ones would be in and around your greenhouse gas emissions. So going beyond then environmental life cycle assessment and the range of impacts we can consider in life cycle assessment, we also want to consider the economic impacts. So we can use life cycle costing. So that's looking at the economy and looking at the costs over the life cycle. So you can determine what the full life cycle costs of a waste management treatment system would be. And we also then can use social life cycle assessment, where we look at the social benefits. And these are typically your local benefits in terms of employment, health and safety, in terms of working conditions as well. So just coming back to life cycle costing, this is very much mirroring the environmental life cycle assessment approach. So with an environmental life cycle assessment, we're looking at all the emissions from the use of materials over the life cycle. With life cycle costing, we're looking at all of the costs of materials, the operating costs, the investment costs. So if you're investing in a new waste treatment facility, within life cycle costing, we would consider the plant costs and the building equipment costs, any land preparation costs, or any indirect costs. We'd have operating costs over the lifetime of that facility, so labor, materials, any pre-treatment costs, any treatment of residues coming out of the waste treatment plant. And then we'd look at decommissioning costs as well. These would consider the environmental externalities. And then we'd look at our projected revenues. So any fees that can be charged due to waste management and sales of any electricity or heat. So we basically add all of those costs up, we remove our revenues, and we get the total life cycle cost. So that's a common way to assess the economic impacts of a system to supplement the information we're getting from the environmental life cycle assessment. Then the third method we're using is social life cycle assessment. So this is, again, we're taking the same approach as the environmental and life cycle costing. We're looking at the full life cycle of the waste management system, but we're looking at the social impacts. So within environmental and life cycle costing, it's often quantitative impact assessment. Within social, it's a little bit different. It's qualitative. So it's a little bit more difficult to carry out this sort of assessment, essentially because we see a lot of differences in local applications of waste management systems. You had very different health and safety procedures in different locations. We'd have different labor conditions. You'd have different numbers of workers and types of workers in different waste management systems in different regions. So it's very important to consider, I suppose, the regional basis, particularly when we're looking at social life cycle assessment, because when we're considering waste management systems, there's important impacts on local employment and also occupational health and safety and health risks for workers in different locations. So this brings us then to our survey. So within the task, we are considering the environmental, the economic, and the social impact of different waste management systems. But what we want to do is to determine which of those sustainability metrics are important for different stakeholders in waste management systems to allow us then to carry out a comprehensive sustainability assessment. We're doing this in different regions because one size doesn't necessarily fit all. There may be different stakeholders affected in different regions, and stakeholders in different regions may have different opinions of impacts and what impacts are important when we consider assessing new waste management strategies in different regions. So what we're doing in the survey is we have it set up in Google Forms. We have a number of questions for you as stakeholders today to essentially give your opinion on the environmental, economic, and social impacts. So essentially, we're going to ask you to rank them between impact levels. So you'll be given a list of different impacts, and you can indicate if you find them either not important to very important. So there's a scale there. And then that'll allow us, and we'll collect all of the data, that'll allow us then to determine a scoring method. So we'll be able to, based on our results from our workshop in Durban, our workshop today, and our workshop in Ireland, we'll be able to determine a scoring system for the environmental, economic, and social impacts that will allow us to say, okay, these are the ones that our stakeholders have said are most important for assessment of new technologies, and then we'll be able to bring that forward in our work in the task. So your participation today is very much appreciated, and I'm hoping that as many of you will complete the form as possible. We will essentially split it up into two parts. So we'll see on the form, section 2 has the following questions. So just to identify which stakeholder group you're part of. And there's a second question to rank which is the most important. So environmental impact, economic impact, or social impact. So what I would ask you to do is after this presentation, if you could answer those two questions, and then you'll see the following questions are related to the environmental impacts, the economic impacts, and the social impacts. So those are more relevant to be answered after our presentations this morning or this afternoon, depending on your location. And again, so this is a North American, I suppose, hosted workshop, but we value the opinions of everyone here today. So please go ahead. I'll put the link to the Google form in the chat. So go ahead and answer these two questions. And then after our presentations, if you could go back to the survey and answer the questions on the environmental, the economic, and the social indicators. Thanks very much.
Thanks, Anyola. So we'll get that link put into the chat here momentarily. As she mentioned, please go ahead and fill those first two questions out right now, if you don't mind. And I'm going to introduce our first set of speakers for today. We have two speakers from the Great Lakes Water Authority, which is one of the largest wastewater and drinking water treatment facilities in the United States. So we're joined today by John Norton Jr. and Xavi Almanza. Both of them are involved in a recently funded Department of Energy grant that is focused on, amongst other things, sustainability indicator identification for a new emerging technology known as hydrothermal liquefaction. So Xavi or John, I'll kick it over to you and let you go ahead and share your screen for this morning.
Thank you, Bo.
Okay. Could I confirm that folks can see my slides?
It looks good, John. Thank you.
There we go. Okay, so I'm John Norton, Director of Energy Research and Innovation for the Great Lakes Water Authority, and Xavi Almanza is our Senior Research Engineer for our wastewater treatment system.
Twice in a couple of months.
You guys could put yourselves on mute. Awesome, thank you. GLWA, it's a nice little contest of which is the largest wastewater treatment plant on the planet. We are on an average dry flow about 700 million gallons a day with a peak of about 1.7 billion gallons a day. Service population about 3 million. We treat about 30% of the wastewater for the state of Michigan and about 40% of the drinking water for the state of Michigan. So about 3 million people on wastewater, 4 million people on drinking water. We generate, it's rough. It varies with time, roughly 400 dry tons a day. If you look at our last 5 years average, this year we're down about 300 dry tons a day. That is still the largest in the United States. There you go. Just so it's a big facility. About 25% of that is land applied after drying, and then about 25% is incinerated, and about 75% is land applied. So here's some pictures of these two systems so that you know that I'm not lying. On the left is our biosolids drying facility. Dries to about 95% solid. So it's an extremely dry material that then gets land applied throughout the Midwest and Canada over to Ontario. Ontario gets about 75% of that flow. So they get about half of our total biosolids, and the rest of it is throughout the Midwest. On the right is our incineration facility. It incinerates, I could say about 100 dry tons a day, or 100 dry tons a day. And the ash is then landfilled. We are looking at a lot of different alternatives. Why? Our incinerators have about 8 to 10 years operational life left to them. Potential staggeringly huge investment to upgrade them due to not only due to their just falling apart, but because we would then be put into a new phase of, or a new status of air pollution control requirements. Just to give you a sense of where this level is here, St. Louis, which is about 130 dry tons a day facility, recently got out, and their low bid for their retrofit was $900 million. So we're talking some really major costs here. We're doing 3 major focuses on research. First is focuses with our research. First is treating the waste and potentially converting it to energy. So it's like, can we treat it to stabilize it, and then what can we get out of it with regards to, with regards to energy? The second, the research effort is regarding emerging contaminants. We're funded by the US EPA as a part of, I'm co-PI on a project here looking at biosolid treatment processes on pollutant loads. The focus of that is land application of biosolids. Obviously, land application of biosolids is the absolute best for the environment. It's a positive to the soil. It's a positive to the carbon. The whole thing is the nitrogen and phosphorus that are contained within the biosolids. It does an excellent job with soil health. And if you compare it to the commercial fertilizers, it's much better for the environment. It's kind of interesting how good it is. But there are concerns. So what's in the biosolids that could potentially be a concern? PFAS is the biggest issue over here, driving significant regulatory changes. And that could very well fully limit our land application of biosolids. That happened in the state of Maine. They were then shipped them much more over to Canada. It's right adjacent to Canada. Canada and the Quebec, province of Quebec said no more. So they were basically having an emergency scenario where they were storing biosolids around on their facilities. And then there were some landfill failures because biosolids are a homogeneous material that just, it doesn't add a lot of strength to the landfill. So there were failures. It was a real mess. And so now they've rescinded that rule, but it's still in political limbo, you might say. One of the things is, just as they've been talking about, there's all these drivers, all these interests in how to do the decision, how to get to what you're trying to do. And it's a very robust science, but it's not very well brought to the actual decision makers. It's more of an academic exercise where it's very academic in the sense of the academicians have been working on decision science for years, but those same processes don't really roll over when the decisions happen in the operating environment. And then finally, there has been, I just want to mention this, we've looked at, the social leadership or the public leadership. We recently formed the Midwest Biosolids Association. It is most of the states surrounding the Great Lakes, plus others that are adjacent to there. So that just gives you a sense of the geography of it, all the way out to like Nebraska and Iowa and such. Then, of course, Michigan, Illinois, Indiana, the folks that are on the Great Lakes. Reason for that is to help focus on just the biosolids aspect as opposed to the larger wastewater treatment aspects of biosolids. So we've been researching into these 3 new to us technologies. Like I say, we incinerate and we land apply. So waste to energy is not a thing for us. We did have anaerobic digesters about a century ago from the late 30s or mid 30s to about the 60s. They've been completely gone for the life of anybody that here who can remember them. So we're looking at anaerobic digestion, where you use anaerobic bacteria to convert the waste to methane that can get either cleaned up and re-injected into the grid or reused on site to combust, make electricity, make heat, combined heat and power. It's a thing. Hydrothermal liquefaction, what we're dealing with there, Dr. Fenoy will talk to about this project in just a little bit. And then finally, we have been looking at pyrolysis, which is like a low temperature, lower pressure, very low pressure conversion technology to make biochar and such. And I joke about it, you basically convert carbon-based feedstock into tar, clogged equipment, and crushed hopes and dreams. I'm not a fan. However, we are funding some research, or we're going to be potentially funding research into pyrolysis. Xavi, myself, and a few others, MWRD Chicago, have already published papers on paralysis. So if we can make it work, which is a thing, that's a big thing. And I talk about the whole operational aspects a little bit later. If we can get it to work, that could potentially be an awesome opportunity for us. The picture there on the right is my baby boy, little Nicholas, 6 months old. And yes, I drink energy drinks. And so my wife thinks this is hilarious to show him drinking my energy drinks. Okay, so anaerobic digestion, this has been done forever. Why are we even looking at it? There's a lot of different opportunities for the front end hydrolysis that'll improve the degradation of the organic, basically break apart the cellulose and the ligands and other stuff that's in the biosolids. Mixing within the anaerobic digestion system is still, I'll say it's more art than science. Obviously, there's some very good mixing systems there, but then there's some trade-offs involved with how those work. And then finally, what do we use for the gas? The best financial use for the gas is to retreat it to pipeline standards, inject it into the grid, and then recover the RINs, the renewable instrument numbers, I guess they're called, which is the environmental attribute value of a fuel, of a liquid fuel. We can also do this for if we generate electricity and sell the electricity with the renewable energy credit. So RECs are for electricity, RINs are for liquid fuels. So we're looking at what do we do? What are the aspects there? Not a whole lot of research, so to say, but investigation from the research team. Finally, pyrolysis, like I mentioned, I'm not a fan of it at all. My dad has done work on it for years, and his waste management efforts, he happened to run the solid waste program for Montgomery County, Ohio. And so I have a clever meme here so that you guys can all scoff. And on the right there is and actually, if you want to go hire these folks, I got this, their senior design project at University of Rochester was pyrolysis and looking at biochar generation. And they got a lot of tar, and there's some tar, and you get tar. And if you can avoid the tar, that's awesome. But the team is a really well-written report. And so I'm really happy to see some of the youngsters coming up that are showing some really clever, real clever thinking around this project. Around this process. We did win its Pollutants and Biosolids Research Award. It's fairly sizable, $1.5 million win. I'm a co-PI, and it's basically looking at take this biosolids. What are the column leaching? What happens when you leach it in a column? What happens when you leach it out on the actual land? Where there's night and day and temperature effects and everything else. What happens with plant growth, and then what happens with plant growth where plant uptake? So those 4 different categories. As you might imagine, I don't actually have it here, but we did expand this project to tie it back to what are the utilities doing that impacts these 3 things. The USCP is not funding that. The Great Lakes Water Authority threw in another $500,000 for additional funding to perform that additional bit of work as well. So fairly sizable project there. The final, not the final, but the near end of my slide set here is just this idea about utility decision making. We had a very nice overview of the factors which go into evaluating life cycle cost assessing, life cycle assessment, these other opportunities or these other aspects from our previous speaker. And the idea is, can we generate a process that is easily used by decision makers? I believe that's the biggest challenge we have, by the way, and is trying to do this. We're about to publish a paper with Danny Coe and Glenn Tiger here on this, but it's very interesting how the factors that drive a decision, or that the factors that others may think are relevant to the decision, actually impact what the decision, or how that cycle then, well, what is actually the driver for the decision? When you're driving down the road and you're starving and your kids are in the back yelling for food, sometimes it's like, oh, I see the Golden Arches, I see McDonald's. It's not going to kill me to eat McDonald's, so that's what we get, so the kids will be quiet and we don't go crazy. It's not the best food, it's not the cheapest food, et cetera, but we do it because it's easy right then. So with that, I want to present something which is, I'd love to have more discussion about this, because this isn't my assessment of what our internal drivers are. It's not necessarily what my drivers are, but what our organization's drivers are. What are our top drivers for the decision-making regarding our biosolids treatment efforts for the next 10 years? Do we go to this? Do we go to this? Do we go to this? What do we do? And it starts on, well, what are the actual drivers for us when we're in the conversations with our engineering team, our operations team, and our planning team? Reliability, meaning uptime, and then how much is it going to take to operate this? Not necessarily costs, like this is a very expensive metal versus a very cheap metal, stainless steel for corrosion versus just a standard carbon metal, but instead cost, meaning the full-time equivalent personnel needing to manage that system. How resilient is it to upset? So now you start to vary load and flow, which is what happens. Will it keep running? And then you work its way down to, I think it would be really cool if we could extract out all the phosphorus that we're having within Ostara or other type of facilities, such as what MWRD Chicago is and others throughout the country are doing. And then I think it'd be really cool if we got this thing to be net energy positive, even perhaps. That's a fairly low number on our, fairly low. We've not had folks call that as a driver. And I just realized I didn't even put in carbon footprint there. That is simply not something that our team has ever said, oh, we got to lower our carbon. That's not a thing. They want to know how many people is it going to take to run it? What's the impact to the regional, the health, air emissions, so to say. We're going to have truck traffic in and out. Those are the things that are driving it. With that, I'd like to hand it over to Dr. Fenoy Almanza to carry it home with this. And like I said, I'm very interested in having some collaborative discussion over these drivers. There you go. So Xavi, do you want to share from your screen, or do you want me just to advance?
Yeah, I would prefer to share from my screen. Thank you, John.
Yep. So I'm going to stop sharing, and there you go.
Okay.
Looking good, Chief.
Okay. Okay. Well, as John was saying, I'm going to talk a little bit more about hydrothermal liquefaction, and I'm going to remind you why we are working on this. No, as John said, we have mainly two treatments for our biosolids, which is incineration and land application. You can see here a little bit of land filling, but that's just for resiliency in case one of these two treatments is having a failure or maintenance. We can send biosolids to the landfill, but we haven't been doing that in the last year and a half for the moment. The thing is that renewing, we might need to renew our incineration soon, and that can cost lots of millions of dollars. We don't know the exact number yet, but we are imagining that it can be between 200 and 400 millions. And that's a lot, right? This is a technology that is treating 25% of our sludge, which is 80 dry tons per day, a lot of solids. And this is why at GLWA, we are looking at different alternatives, like John has said, And I'm going to talk specifically about hydrothermal liquefaction. Since I don't know very well my audience, I'm going to explain a little bit what is hydrothermal liquefaction. And basically, it's a process where you can feed your sludge with a 20 to 30% of total solids, and you treat it at 360 degrees C and 210 bars. With this, you mostly generate two products. You generate a biocrude that can be transformed later by a refinery into a transportation fuel. And also you get a solid precipitate that might have a high concentration of phosphorus, and maybe you can convert this into a fertilizer later on. This technology has other advantages for GLWA, right? It can reduce the sludge volume by 80 to 90% in only 30 minutes. And this comes back to low footprint, right? Like what John was saying earlier. Also, it can accept a diverse range of wet waste. It's not only a sludge, you can feed also fog, fats, grits, and oils, and also food waste, or maybe even also agricultural waste. So you can feed different types of wet waste. And even plastics, sometimes some sorts of plastics and paper waste can also be fed here. We also wonder if this technology maybe has a potential to destroy emerging contaminants. We have heard John talking about PFAS earlier, right? And maybe these conditions of 210 bars are hard enough to destroy a majority of them. And here at the bottom, I have put some references that we have published in collaboration with the Pacific Northwest National Lab. So you can see a little bit of the research that we have done on hydrothermal liquefaction. And here at the bottom, there is also a techno-economical analysis that we have done for this technology being implemented in wastewater treatment plants. One of the research that we have done with hydrothermal liquefaction at GLWA has been to look at the aqueous byproduct that you generate with HTL. You generate an aqueous byproduct here that, you know, if you implement this in a wastewater treatment plant, you can think about sending this back into your biological process or the headworks of the wastewater treatment plant. However, this effluent has a high concentration of aromatic organics that are very hard to biodegrade by conventional microorganisms. So we need to be careful about that, right? So if we implement this technology in a wastewater treatment plant, how should we deal with this, right? It's an important question. And maybe this is why hydrothermal liquefaction hasn't been implemented yet at the full scale, is because of this problem, right? So here at GLWA, we have treated our sewage sludge through hydrothermal liquefaction. This has been done in collaboration with the Pacific Northwest National Lab. And they have sent us back the aqueous phase. And we have performed experiments with a new type of anaerobic membrane bioreactor. You can read more about this anaerobic digester in this reference here. And basically here, what we are using is a new type of membrane that generates a high concentration of biofilm. And in the literature, we have seen that biofilms can treat HTL aqueous phase more efficiently than other systems. I'm not going to talk more about this due to the time, but basically what we are seeing so far with this experiment is that you can treat this HTL aqueous phase with this new type of anaerobic digestion, but you need to do co-digestion. You cannot only treat this HTL aqueous phase by itself. You also need to do co-digestion maybe with sewage sludge to bring the right amount of nutrients for the microbes to grow. One important part of my presentation is going to be this project. Here at GLWA, we got 1.5 million of funding from the Department of Energy of the United States to perform a feasibility study for hydrothermal liquefaction. This is a project that we are not doing alone. We are collaborating with all these entities, especially the Pacific Northwest National Lab, Wayne State University in Detroit, University of Michigan, and many others. And I can say that this project is divided into 4 tasks. So I'm going to talk a little bit about the 4 tasks now, but the main goal of this project is to try to figure out how feasible is to implement hydrothermal liquefaction in the wastewater treatment plant in Detroit. What are the best business case scenarios and what can be unintended consequences of doing so? The first task really is about finding what available organic waste we have around our wastewater treatment plant. Earlier, I said that we can feed sewage sludge in hydrothermal liquefaction, but also other waste. So we are looking at how much food waste we have around, yard waste, paper waste. We are thinking also about using waste from fast food restaurants, where you have a trash bag that's going to have food waste, but also some plastic or paper from the mill, right? That might be that HTL might be able to treat, and that can be a good source of energy. After looking at the quantities and types of waste that we have around, we are going to characterize the waste that we think are going to be more optimal for hydrothermal liquefaction. And with that, we are going to come up with at least 4 wet waste blends that we want to treat in hydrothermal liquefaction. Task 2 is about determining sustainability indicators of our current practices. We want to determine economic, environmental, and social indicators of our current waste management practices, and also of HTL in different conditions. So with that, we are going to perform techno-economic analysis and life cycle analysis to determine what are going to be the most optimal waste to energy scenarios when implementing hydrothermal liquefaction in Detroit. But then another important aspect that we want to introduce in our project is an environmental justice aspect. We also are trying to perform I don't know if I should call it social life cycle assessment, but basically what we want to do is to communicate with the communities around the wastewater treatment plant and communities in the city of Detroit. We don't want a technology that works perfectly well, but has some burdens, and install this technology in a neighborhood and kind of bother the neighbors around, right? So with this task, what we want to do is to have workshops to communicate the project to community groups in the city of Detroit that represent citizens that care about waste management. And we want to identify what are the needs, concerns, and trade-off that these community groups have. But we're not going to only talk to community groups. We're also going to talk to stakeholders as well. Like if we're going to bring food waste, we might want to talk to waste management companies. We want to talk also to refineries, because these are the ones that are at the end of the day going to take our biocrude, right? And we are going to collect this feedback, all this communication, and incorporate it into our models to find the best way to implement hydrothermal liquefaction in Detroit. And this task does not only has this, we also want to educate on resource recovery and waste management, the future workforce of Detroit. And that's why we're also developing courses for the Wayne State University and also DAPSET, which is an organization that works with high school students in Detroit that are normally not well represented in universities. The last task is about bringing a demonstration unit at our wastewater treatment plant. And this demonstration unit, what it's going to do is to take these 4 feedstock blends that we have characterized at the beginning of our project and feed them into the hydrothermal liquefaction demonstration unit and see how well it does with this waste. At the same time, we are going to have tours to demonstrate to other facilities like other wastewater treatment plants in the countries, the community groups, stakeholders, how this system works. And if people in the call here are from the US, feel free to email me if you want to see this demonstration unit that will take place at the end of 2024. And of course, this is kind of an experiment too, right? We are going once we have this demonstration unit, we are going to characterize the biocrude and the effluents, and we want to study the fate and transport of PFAS during hydrothermal liquefaction. We are also performing studies on how to treat this aqueous byproduct I was talking earlier. We are going to do the studies with anaerobic digestion and also with supercritical water oxidation. And at the same time, we want to evaluate what is the impact of recirculating this aqueous byproduct to our biological process. As you can see in this picture, we would like to have a lab setup in that is going to imitate the activated sludge process. And we can see how well it does at getting this HTL aqueous phase without treatment, but also after treatment. And this is the end of our presentation. Thank you very much for listening. And also I would like to thank all these collaborators for the work done with us at GLWA. Thank you very much. And if you have any questions.
Thank you, Xavi. Thank you, John. So we are going to start our first breakout, and we're going to shorten this briefly just to kind of catch up on the schedule a little bit. So we'll do the first breakout as 10 minutes, and myself and Finola will be kind of moderating those two breakouts. So you've already been pre-assigned to a good segue. I do want to kick over now to Tatiana and Ulysses, who are going to talk a little bit about their life cycle assessment work. And I think that, that should be a nice dovetail into what we were just talking about with regards to your plastic wrapper, or air quotes, compostable fork there. So Ulysses or Tatiana, do you want to share your screen? Okay, great.
Yes. Can you see my screen?
It is loading. 1 second.
Not yet, no. Now.
Yes, we see it.
Working? Excellent. Well, thank you very much, Abel, for the introduction. So we are Tatiana Benavides and Ulises Gracida from Argonne National Laboratory. And now we're going to shift from the economic sustainability to the environmental sustainability. So we will be touching base in some of the aspects that are important when we are focusing on these technologies that can process waste plastic and organic waste as well from the environmental perspective. So as we know, there is many important issues associated with plastic, specifically for plastic, which are the increased amount of plastic waste that is being generated over the years, and that is not expected to reduce because of the increase of the production practices and consumption practices of the society. And also, we are also aware of these many issues that are happening related to the environmental issues, specifically to the oceans, where we can see a growing amount of these microplastics that are polluting the oceans as well. And that amount is also expected to increase over the years. And also, when we are considering organic waste, we know that there is like a lot amount of food waste that is never processed. Like, according to the FAO, 1/3 of all the food produced is wasted and is not reprocessed in many ways. And also, we know that these associated emissions with the organic waste disposal are responsible for around 100% of the world's total emissions. So therefore, there is this important issue of finding technologies to reduce this consumption or reduce the amount of plastic waste that is generated. Specifically talking about plastic waste, there are several technologies that we could apply, which we tend to call them recycling. We have mechanical recycling first, when we use extrusion or thermal processes to convert this post-use plastic into recycled resins that can be used again on the manufacturing of packaging materials, for example. And we also have advanced or chemical recycling technologies. What they do is they convert the post-use plastic back into the original chemical components that originated the plastic at the beginning. So we can therefore use post-use plastic, making these chemicals, and then produce new plastics. Some of the technologies that we have analyzed through our in our team at Argonne are focused on two major processes that I'm going to talk about, which are pyrolysis, which is precisely, John and Xavi mentioned a little bit of that in their presentation, which is the thermal degradation of the feedstock into different components, which can be solid, liquid, or gases. And also, we were able to analyze the effects of other technologies to compare plastic, like, for example, from a bottle-to-bottle pathway, where we can use other technologies like enzymatic hydrolysis or methanolysis. Another important aspect is that there is a wide range of products that we can obtain from this produced plastic, ranging from fuels, intermediate chemicals like pyrolysis oil, and very interesting move from the technology is the production of plastic, something that was also mentioned previously, that this concept of using these intermediate feedstocks that can be co-fed with conventional feedstocks to produce new plastics as well. And also some technologies where we can expand the boundary to include not only the chemicals manufacturing, but also the end products, like in this case, when we analyze the bottle-to-bottle conversion. When we do the analysis or the life cycle assessment to estimate the environmental impacts of these different new technologies, we can consider different approaches. Some of different approaches, apart from estimating the impacts of the new technologies that we can see in this blue square, they also account for comparisons within conventional technologies. For example, these fuels and these other products or chemicals or plastics are already produced in large scale, so therefore they have emissions associated with that. So we want to compare how these new alternatives are efficient in reducing certain impacts compared to these conventional technologies. And another aspects that we can consider are the current practices for waste management. Like, for example, mostly what we know is that landfill or incineration are the strategies that are mostly used around the world. And therefore, we can either make comparisons of these new technologies with the usual waste management conversion, or also include credits from avoiding the traditional waste management of these alternatives. So after having some background about what are these technologies and how we can analyze them, now we're going to talk a little bit more about the different impacts that could be used for the evaluation of these new alternative technologies for handling plastic, post-use plastic. So greenhouse gas emissions, as was also mentioned before, is the most widely used impact to estimate how much of these greenhouse gases are emitted based on the different stages of the conversion processes. And as I mentioned it, and I was mentioning before, there are different types of products that we can obtain from these different technologies. So it's very interesting to see how the differences between the conventional production and the alternative production are happening based on the type of product. Like, for example, when we use post-use plastic to produce fuels, we can see that the greenhouse gas emissions are very similar. There is not really too much of improvement when we do the comparison of the performance of these technologies. And when we move towards the use of post-use plastic to produce new plastic, what we can observe is that definitely there is a range, depending on factors like, for example, the plant capacity. Like, for example, pioneer plants have higher greenhouse gas emissions of the plastic produced compared to the conventional production, while when we go to more optimized technologies or higher scale technologies, like what happened in the end plants, we can observe reductions in the greenhouse gas emissions compared to the conventional production. However, there are aspects of the process, as you can see here, that are important for the evaluation. Like, for example, here we are just testing differences in the co-feeding rate. Also, yields, we have found that yields are an important component for the comparisons of the greenhouse gas emissions. Like in this case, we can see how there's like an important reduction of the greenhouse gas emissions when we consider the yields, and also other aspects like sources of materials, for example, hydrogen on electricity generation can also play an important role in the performance of greenhouse gas emissions of these different new technologies. Another important level, and it's something that I guess was mentioned in the questions that we were having on the breakout rooms, were like how we can better track the flows of materials and how we can better understand the effects or the implications of these different technologies. Well, we can have a traditional technology level approach when we just compare the different technologies among themselves. Like, for example, here in the bottom three technologies represent these alternative technologies compared to the conventional technologies specifically for this plus related to polyethylene terephthalate. And one interesting thing that we can observe is that don't necessarily these alternative technologies will lead to lower greenhouse gas emissions. So therefore, with these impacts, we can identify what are some of the stages that require improvement. But what happens when we go through a system levels approach? We need to better track the flows of materials, something that was specifically mentioned in question 2 of our breakout room, where we can use material flow analysis and life cycle assessment together to analyze what are the differences of different impacts related to the implementation of these different circular economy strategies. Just as a brief takeaway from this graph, we can observe that maximizing, in this case study, maximizing mechanical recycling can reduce emissions, while including other techniques like advanced recycling will result in similar emissions from the systems level approach or value chain perspective. Moving from greenhouse gas emissions, another impact that we could analyze is fossil energy. Fossil energy is associated with the energy from these fossil-derived or petroleum-derived feedstocks that are used for the production. Something very interesting that we can see also the effects of different products analysis. We can see that for fuel, we reduce considerably the fossil energy because the plastic that is used to produce fuels can be considered burden-free from the energy because the energy has already been used for the production of the plastic in its first life, for saying so. And then when after the post-use life, then we can use it for fuel production, and we don't need to account for that fossil energy from the feedstock. While, for example, when we are analyzing plastics, we don't have as much reduction as we can see in the fuel analysis, but we still can see considerably reductions from the fossil energy perspective because plastic waste or post-use plastic have considerably lower fossil energy associated compared to conventional feedstocks like naphtha or gases that are traditionally used for the production of plastics. Another important metric is water consumption. We have heard issues about water scarcity. We just recently listened that regionalization is important. So water consumption might play an important role in those regions where there is this lack of water resources. So something that we have found is that it's interesting to evaluate this technology because, as we can see, some of those technologies can have higher impacts on water consumption compared to other ones. And when this information from the process level analysis is translated into the systems analysis, we can see how this can affect the overall water consumption of the supply chain. So therefore, it's important to track the water consumption and also to identify areas of opportunity within the new technologies to reduce also the water consumption associated with the processes. And moving forward from some of these metrics, we also are thinking about circular economy. What are some of the benefits that we could obtain from this technology from the material flow perspective? Well, one of these first metrics that we could use is definitely virgin material use, which evaluates the amount of material that is introduced in the system, which is requires the extraction of virgin fossil-based resources. Evidently, when we have recycling technologies that bring back this post-use plastic into the system, we can reduce the use of these virgin-based materials, as you can see on this graph. Like we can, once we apply these circular economy strategies, we can see the reduction of this virgin use of the materials because of that. And apart from that information, we can also be able, when we combine different metrics, like for example, greenhouse gas emissions with, for example, virgin material use, we can observe that the implementation of the technologies will show some trade-offs, as we can see in the plot below. Like some of these technologies that actually can reduce the greenhouse gas emissions in the supply chain, well, they are not precisely the most efficient to reduce the virgin material use. And on the opposite side, those technologies that can considerably reduce the virgin material use might not be the most efficient in reduction of greenhouse gas emissions. So that's the importance of the use of these different metrics. And finally, we can consider another metric, which is solid waste generation, where we can actually track the material losses within the system that will end up in traditional waste management, like landfill or incineration. So definitely, again, those alternatives that favor circular economy can considerably reduce the solid waste generation, as we can see on these plots, or for a process level approach and a systems level approach considerably compared to the conventional production, because we are not needing those virgin fossil-based feedstocks anymore. So now turn to Tatiana.
Hi, yes. Can you hear me? Good. So now I'm going to talk very quick about the counterfactual scenarios, because these are very interesting aspects when we do analysis on waste feedstocks, plastic or organic waste into new products, because they can determine or change the GHG emissions. So what Ulysses was talking in the beginning, the example of the plastic to fuel or plastic to plastic, we provide a set of results regardless the way that we allocated the emissions, either energy or market, or regardless the size of the plant. You saw the different results or benefits, but when you include the counterfactual or business as usual emissions that will be avoided if you use these new technologies, if you have a scenario, for example, in the US, when the majority of plastic goes to landfill, and it is considered that plastic is very stable, because we were not dealing with bio-based plastic or biodegradable plastic, sorry. So the plastic is stable in the landfill, and then all the carbon in that plastic will remain in the landfill, so it's sequestered. But only 17% will be incinerated. So those emissions from incineration will be taken into account as credits for this new technology. And when you take that into account, you start to see benefits. But when you switch from waste management in the US to like in the Europe case, when it's kind of like the opposite, when the incineration in this case is 63%, then those emission credits will be higher than what we have in the US. So you see how different scenarios will be depending on your counterfactual analysis. And in the next slide is the same example for the plastic to plastic. Yes. So here you will see, if you click again 2 times, Ulysses, that the reductions are significant when you start including the counterfactual scenarios, but it's significantly higher when you include the scenario for the Europe, because you have more credits for the waste conventional waste treatment. And the figure on the right, that's another example that we didn't talk, but it's more talking on the waste feedstock management. When you turn food waste, I believe, via anaerobic digestion, and then you upgrade the volatile fatty acids or BFA that are result from that into different fuel products, gasoline, jet fuel, and 2 types of diesel. And you can see that we're presenting different bars and comparing into conventional petroleum-based fuels. You see that when you have the conventional waste treatment of this is based on the landfilling. And if you change your parameters for the landfilling gas capture from the conventional 59%, you have lower emission than the conventional petroleum base. But if you switch this to stream cases where, for example, you have high capture of the landfill gas, like 80%, your results are going to not be very beneficial compared to the conventional waste, conventional petroleum-based fuel. And if you go to the opposite case, when it's 0% of this landfill gas capture, then your emissions will go very low, even like to like 300, depending on the technology. But one interesting aspect here is that the yields of the technology. So if you're having better yields, that means you're going to use less biomass or waste feedstock to produce the same amount of fuel, depending on the technology. That means that your counterfactual scenario won't be that beneficial, because since you're using less feedstock, you're not going to divert that feedstock, a lot of feedstock, from the conventional waste management. So that was the trade-off in this study. And I listed the citations for the papers if you wanna take a look at a little deeper on that. So now I can just go very quick on the organic waste. So the tool that we use to conduct this analysis is called the GREET, the Greenhouse Gas Regulated Emissions and Energy Use in Technologies. And we have a lot of different technologies for waste to energy, and we apply a holistic approach to address these counterfactual scenarios, because we need to evaluate what are those emissions of these associated business as usual or counterfactual scenarios in order for us to account for those avoided emissions. And grid has different technologies, different feedstocks from landfill gas, animal waste, municipal solid waste, and wastewater sludge, to different conversion technologies. Of course, the AD fermentation and hydrogen liquefaction. So those are the technologies that we work with other national labs like PNNL and NREL, and they provide information and the parameters, and we update all those technologies into our system to different products like from natural gas, chemicals, ethanol, and hydrocarbon fuel. So in the next slide, I will present just an example of how we set the analysis, especially for the renewable natural gas. So we have this system boundary. First, we need to identify what is this business as usual waste management practice. And on the previous presentation, they were just putting some examples from landfill and anaerobic digestion. We identify what are those emissions from the carbon, like CO2 or methane, the different wet waste, the production for energy, the conversion technology. So identify what are those energy consumption, the leakage and the upgrading systems, and the residues, and understand what is that residue, what is the fate of that residue, and if we can use it for displacement of fertilizer, what's the carbon content, because if you end up in the landfill, then you will have portion of the carbon sequestered, but another portion will be emitted. So the distribution and use is also part of what our system analysis, system boundary will contain, regardless is for vehicle operation for light duty or heavy duty. We have all of the parameters needed for those analyses, and or if you use this renewable natural gas for process fuel or heating up buildings. So in the figure, yeah. So here, if you just go quickly, Ulysses, is just showing what are those key questions or key issues that with the grid modeling we can solve. So again, identify what are the business as usual for waste management, then identify what was the energy consumption, material and energy in general, and for the conversion of the feedstock and upgrading, and identify what is the fate for this solid residue, and what are the chemical or components of this residue. And when we do the analysis, the next slide, Ulysses, that is showing here. So I'm just presenting here very quick different feedstocks for different natural gas pathways, the compressed natural gas or liquid natural gas. But the main point here is you see how the different numbers for the GHG emissions will vary depending on the feedstock and the technology. And here we're showing also those key questions, like from the business as usual, you can see that if you're treating swine manure, you will have more credits if you avoid those emissions from the conventional treatment than if you work with sludge. But on the other side, when you look at the conversion of sludge, it's very energy intensive. It needs a lot of energy to process all the sludge, reduce the moisture, all of that. And then the trade-off will go that the emissions are driven by the technology. And in the third question, which was regarding the solid waste, you see that if you treat these solid wastes as a co-product and you understand what are the properties, the nutrient content or the carbon content, then you can see what's the fate and what are the benefits that this treating this co-product will bring into the technology. But again, you have to be careful on how you're going to displace those credits in the different technologies. So the last slide, it's interesting because that one is a study that we have that discusses the GHG emission reduction impacts of the combination of different waste feedstocks with different products. And here we compare the renewable natural gas in the figure on the left versus producing lactic acid, which is a precursor for polylactic acid, a bioplastic. And in all the scenarios, you can see that you have lower emissions than the traditional petroleum-based counterpart, like either natural gas or other ways to produce lactic acid. Even in the lactic acid, you have all negative values for the GHG emissions because the majority of this, or the driver is the counterfactual scenarios and the avoided emissions from those. But it is important to look at what is the impact of doing this analysis and the impact of this GHG emission reduction. So this work is also interesting because it shows that the carbon intensity of the GHG emissions alone cannot be used to demonstrate the sustainability of a product generated from different waste feedstocks, because if you see the figure on the right, you see that we're comparing the GHG emission reductions, but taking into account the potential of production of these chemicals, like either the renewable natural gas or the lactic acid. And for renewable natural gas, we have a lot of feedstock that can be converted into natural gas, and this natural gas can really supply the demand. But for the lactic acid, even though we have a lot of feedstock that can be converted into lactic acid, I believe will be, based on our calculations, like 37 million metric tons. The demand of lactic acid right now is not that big. It's actually, last year was less than 2 million metric tons. So the market will be saturated very quickly, and there won't be that much impact when you turn these waste feedstocks into lactic acid. So looking at the impact of the production or market potential is important when you're also tidying these environmental metrics that we're analyzing here. So the last slide is just the summary. I think I went over the time. I'm not going to repeat, but this is all the key messages that we provided through our slides. If you have any questions, we provided our emails at the end of the presentation. I think I'm done.
Yeah, thank you both. That was great work. And I think that sets up nicely to talk about various kind of other indicators that, depending on the waste that you're working with, might drive a decision making. And so, yeah, thank you for kind of giving us the survey of different analyses and tools that Argonne is working on. So we're going to go ahead and go into breakouts again. We will do that again for about 10 minutes. Okay, now certainly last but not least, we are going to, and I know this has kind of been like a whirlwind of different talks, but we certainly want to make sure we were talking about siting and some of the human elements of waste management, given some of the siting challenges that these facilities face. So our final speaker of this workshop is Dr. Corinne Scown of Lawrence Berkeley National Lab, and she works with our data modeling and analysis effort and program. So she's going to be sharing some of her work that she's done over the last couple of years, and hopefully share a few bits from her tool that she and her team has been developing. So Corinne, I will let you go ahead and take it away.
Awesome, thanks. Do I need to try and shorten my talk? I know we're running a little behind, or should I go the full 20?
I think you're fine. I think
Okay,
you're
awesome.
Good, full 20.
All right, so social sustainability and siting, last but not least, let's go. So just a brief introduction on kind of my background. A lot of the discussions today have been very familiar. We do work in TEA, LCA, kind of land use analysis, siting for bioenergy, for plastics recycling. And so this is very much like my sweet spot. I'm so happy to be here today. And we've also done some work with specific companies that is kind of, I don't know if we technically call it technical assistance, but sort of working with individual companies in California. So here's an example of this work we did with the Zero Waste Energy Development Company, and I'll be bringing up that example from time to time. I have a disclaimer up here that even though we're talking about, can everybody mute themselves if you are not talking? Okay, so I am not a social scientist. I am an engineer. And so when I start talking about social science stuff, take that with a grain of salt. And I will do my best to stay largely in things I know that I know about. So first, as Bo mentioned, we do have this web tool, which you're all welcome to go check out. It's biositing.jba.org. So you can see the URL down on the bottom. But this just kind of gives us an idea of what's going on in the US. It's gonna be a very US focused talk, because that's where most of our research is. So this is the distribution of plastic and organic resources around the US. So that's like crop residues, organic waste, plastics, and then kind of some of the relevant facilities that are around, like wastewater treatment facilities, MRFs, et cetera. So you got to get a feel for how it's distributed. I mean, most of the waste is like, it's where the people are. And then we have a lot of ag residues in the Midwest because that's where a lot of the agriculture is. So when we think about building facilities that convert this stuff, there are obviously some big benefits associated with diverting some of this waste. We've talked about them today, right? Diverting organic waste from landfills can mitigate methane emissions, especially in landfills that don't have gas capture systems at all, or they don't have efficient gas capture systems. You're emitting a lot of methane. Even if you do have a gas capture system, methane gets emitted from that waste that decomposes quickly before the cell is capped off. So I think it's kind of a fairly common misconception that if you have a gas capture system in a landfill that you don't emit any methane. You definitely do. Diverting forest residues, for example, can mitigate wildfire risk, and that has these kind of knock-on benefits, air quality, property risk, et cetera. And then nutrient runoff is a huge deal. So that's the reason why we can't apply biosolids during the rainy season in California. Some years we barely have a rainy season, but this is a concern. And if we can divert some of this waste, we can mitigate it both from organic, sort of mixed organic waste, but also from things like manure. But the benefits and the risks may not be borne by the same communities. And so it's important to think about where we're going to put these facilities so that we have feedstocks we can leverage, that we can beneficially divert. But we also have to kind of keep track of who's getting the benefits and who's bearing the costs and the risks. So I'll give you an example. And these are some draft results, kind of early results from the Roads to Removal report. This is just one example, but that report is focused on using organic waste for what's called bikers. This is basically like capturing as much of the carbon from organic waste as possible, sequestering CO2 underground, and then maybe you're generating like biohydrogen. That's a very common pathway that comes up in that report. So if we looked at like where the air pollutants would get emitted when you start to build these facilities out, you can see the distribution is largely kind of the eastern portion of the US, some in California. And then in terms of where the human health damages would occur, basically eastern half of the US. And this includes forest residues. And one of the biggest air quality benefits that you would get from implementing this strategy at scale would be in the mitigation of wildfire risks. And it's almost like the total opposite of where the air pollution costs are. And so this is just to kind of highlight this high level point that, those don't always align. The communities that bear the benefits in this case may not be the same ones that are seeing increases in pollutant emissions. The other thing that we have to keep in mind as we start looking at where to locate facilities, and it's something that we haven't talked as much about today, is that if kind of carbon management and carbon sequestration are going to become big drivers, both environmentally, but also economically, right? If you're selling carbon credits, then we have to keep in mind where the feedstocks are, but also where there are opportunities for carbon capture and sequestration. So you can see this is a map of kind of confirmed geologic CO2 storage locations across the US. This is, again, these are draft results from the Roads to Removal report, overlaid on just a map of like land cover in the US. One of the things that we learned through this analysis is that there's kind of a rule of thumb, or if you're primarily producing like liquid fuels, if more than half of the carbon in your feedstock is going to go to a product, then you should locate yourself near the feedstocks, right? But if more than half of the carbon in your feedstock is going to go to CO2 that you inject underground, then you may be better off locating where the geologic storage is rather than where the feedstock is. Obviously, there's all kinds of extra nuances depending on the mode of transportation, et cetera, like rail, it's cheaper than truck if you're going a long distance. But this means, we have yet another layer of complexity in like, where do you put this stuff? So we have to keep in mind what communities we're putting it in, what feedstocks are available locally, but now also, if I have CO2 to inject, can I inject it on site? CO2 pipelines come up as something that may be required as supporting infrastructure for these facilities. And those have yet their own siting concerns because people can asphyxiate if you release a lot of CO2 into the atmosphere. And so that is definitely a worry. Okay, so moving on to plastic waste. This is something that we've also been doing some work on and chatting with the Argonne folks. We had a funded sort of in a series of projects that all started and ended around the same time. We looked at like where the plastic is in the US. And so if you were going to start locating facilities to either do energy recovery or ideally recycle some of these, where's the material? And what kind of infrastructure do we have right now to collect it and separate it? So, you know, big takeaway on where the material is, it's largely where the people are. Like they're the ones who are generating the waste. There's some like post-industrial kind of pre-consumer waste that's more concentrated where the manufacturing facilities are. But that'll tend to be a lot easier to convert because it's very clean. Often it's like literally one material, you know exactly how to recycle it. But in terms of the stuff that we recover from mixed streams, well, you know, like in most places, less than 10% of all the plastics are actually making it to material recovery facilities and getting sorted. And so this means that in addition to investing in the actual recycling or conversion facilities, we also have to invest heavily in additional sorting capacity to get that stuff out of the waste stream so that we can convert it. There's an interesting trade-off, and I think this probably applies beyond plastics, but basically when we started developing these scenarios, and this is stuff that's not published yet, but it's under revision for a journal, if you do less sorting and pre-processing, so you end up with more mixed streams, you're going to end up erring on the side of facilities that are like thermochemical, right? Like you may be doing pyrolysis and you get like naphtha back and you can crack it and get ethylene. Whereas if you invest in more sorting capacity, you can do more mechanical recycling. You can do more of these recycling processes that yield something closer to like just back to like monomers or polymers that you can use. And so there's kind of this trade-off in like, what infrastructure do you want to invest in? You know, do you want to do more sorting facilities and then enable kind of more like closed loop recycling, maybe fewer of these like harsh high temperature processes? Or do you want to skip the investment in additional sorting infrastructure and just handle those mixed bales? And I don't think there's necessarily an easy answer one way or the other. But this applies to organic waste as well, right? Like these mixed feedstocks are generally going to be easier to process if you're using a sort of harsh high temperature process. And you know, like the bottom line is like we have to invest in a lot of new infrastructure, no matter what strategy we choose. But this is also not going to happen in a vacuum. So there are going to be massive changes happening. I mean, this is the US, but this is true globally as well, to support the kind of broader push toward decarbonization. And so in some cases, we may be able to piggyback on infrastructure that's going in that supports this transition. In other cases, we may be, you know, competing in interconnection queues, you know, competing for land area, competing for limited like financing dollars. So, you know, it's going to be a really interesting time. So going from the macro level to the micro level, I'll talk a little bit about some of the work that we've done in California on waste conversion. So we worked with this facility, which I'll call ZWED. And this was a high solids anaerobic digestion facility. So the picture is up on the top right. And we basically got involved in like every aspect of their operations. They were a total open book. We saw all of the financial details. We took measurements to figure out what kind of like fugitive methane emissions, other VOCs were coming from the facility. We tracked the material and then took measurements of like air emissions from the composting facility where they ultimately sent their stuff. And then we've been, you know, sort of doing similarly detailed work on the plastic side of things and talking to Cal Recycle to understand kind of as California pushes towards zero waste, tries to divert more material from landfills, like what that means for the surrounding populations. So these are some of the basic things that we always think about, right? There's two general categories. There's like, what do we know about the location where we're actually putting the facility? So do they have pre-existing health burdens? Do they have pre-existing resource constraints, like water concerns? How close is that proposed facility site to vulnerable populations? You know, schools, facilities where elderly people live, that kind of thing. And then there's all the stuff we know about the potential facility, right? The level of truck traffic that it's going to generate, noise, freshwater consumption, any kind of wastewater discharge, nutrient discharge or runoff, air pollutant emissions, odor. These are all things you have to keep in mind. Now, I will say there are some really wonderful data sets out there. If you haven't checked this out, and again, this is very like US centric, but the EPA has a site where you can access some of these metrics. These are literally screenshots from the screeningtool.geoplatform.gov. And they've assembled a lot of this information. By the way, I'm not looking at the chat, so if you guys have questions in the chat, I will look at them as soon as I'm done. And so, you know, these are, I would say, like, they're sort of not hard data that are aggregated up into these more qualitative categories in some cases, but it can be incredibly useful as just a preliminary screen. Like if I'm coming up with some big strategy for scaling up a particular conversion technology, you know, am I inadvertently burdening some communities over others? So I find this to be really helpful. I definitely encourage you to check it out. And so we've integrated this into our biositing tool. So these are what are classified as disadvantaged communities in the US. The original data, as I mentioned, came from this screeningtool.geoplatform.gov. That is publicly available as well. And you know, you can kind of see a lot of the places where we have biorefineries now are not classified as disadvantaged, right? We've got a lot of stuff going on in the Midwest. But a lot of the places where you might have seen in the earlier slides that I was showing, we want to do build out kind of in the Central Valley, California, and the Southeast. You know, then we want to be careful about how we're burdening these communities. And so one of the things you can do is kind of visualize, like, map out your choices for what areas are or are not in play for development. So this is an example of how we selected what land was available for development of these bikers facilities, biomass with carbon capture and removal. And you know, you say, okay, protected land is out, right? We're also not going to build on wetlands. We're not going to build where there's already developed land because there's something already there. It can't be too sloped, and you can see these types of land getting sort of peeled off and set aside as like, we're not going to build there. Okay, places that don't have enough water, so that's not within stream flow, we take those out of the equation. And then kind of what are you left with? And you can look and see, you know, how does this shake out between like disadvantaged and not disadvantaged communities? And so this is an example of how we were able to keep track, and it ended up being kind of about evenly split, you know, a little bit more not disadvantaged communities. Other metrics that you can keep in mind, you know, current water stress is not future water stress. And so we do have to start relying at least partially on projections for where we think water scarcity is going to occur in climate change. And so this is some nice data that we ended up using actually for the roads to removal report. The other thing we can keep in mind is like, where are these non-attainment zones? So we think a lot about particulate matter concentrations and emissions, but we also have to keep in mind that there are other things like ozone that aren't the primary driver for human health impacts, but we kind of want to understand like what communities are already, you know, facing disproportionately bad air quality. So there has been some prior work kind of asking residents, like, what are you most concerned about? This is funded by the USDA. It was specific to biorefineries. And I thought it was really interesting because the thing I hear from people on the ground is like, people mostly care about truck traffic, like odor, if it's a problem, noise. But the opponents, like, they cited all of these really macro things that they cared the most about, like, you know, long-term environmental impacts that I get. Biofuels not being economically viable. I was really surprised that that rose to the top as like one of the biggest drawbacks. You you would think that that would not be at the top. So kind of interesting food for thought. The other thing to keep in mind is that each site is unique, so it's really hard to paint with a broad brush and say, like, these are the impacts that everybody is going to care about. So this is an example. This is also a publicly available tool from LBL. It's just smelly.lbl.gov, very easy to remember. And it was part of the ZWIT project where we did dispersion modeling and looked at kind of odorous emissions and who would sort of be above that like odor detection threshold. In this case, it's for hydrogen sulfide. But local meteorology, time of day that the stuff gets emitted, that all factors into who feels these burdens and when. It can also be hard to you can get confused when there are multiple facilities that all have these same kinds of impacts. So they are near a landfill, a wastewater treatment plant, and sometimes you get blamed when it's not your fault. And this is just something that happens. So mitigation measures, again, you have to use these sort of place-based strategies based on what is really going to impact the community the most. But examples like electric trucks, so they're not emitting, they're quieter. It may be like reducing flaring by switching to a system where you're upgrading biogas and injecting it in pipelines rather than burning it on site. Additional emissions control technologies, community engagement, like early and often, and do it in the languages that your local communities speak. This is like a really common, seems like kind of a silly mistake, but we've seen this happen. They do it all in English and most of the people there speak, Spanish or Portuguese. So, takeaways, just we have to keep track of environmental justice and siting constraints from like the very macro level all the way to the individual facility level. And just because the challenges are unique to individual sites doesn't necessarily mean that we shouldn't start tracking it earlier. So, and the reputational risks are highest in these early stages. We start to build stuff out. So we really have to dot our I's and cross our T's and do a really, really good job of making sure these facilities are beneficial to their local community. So with that, I'll stop. I think we're about on time.
Yeah, that was great. Thank you, Corinne. We're getting close to the end of the time, so rather than going into breakouts, I thought it just made sense for everybody to kind of stay in the main session. But if anybody would like to ask any questions of Corinne or bring up anything else with regards to kind of the social sustainability challenges, one question I had for you, Corinne, to maybe kick off some questions would be, are there particular data or like data transparency methods that you've seen that have worked particularly well? Because I think we see that come up a lot as like a best practice or as like a worst practice, which is to like share information about how a like site is going to impact. And I'm curious, like what sort of data are they sharing with the community, and what is the community maybe asking for to see?
Yeah, it depends on the stage of the product. I mean, obviously they do these like environmental impact statements, and the groups, especially if the groups are in opposition to a project, will really pour over those details. We like many years ago, I was involved in a project where we were talking to community members who were opposing an LNG terminal in Fall River, Massachusetts. And like, they knew the details of that facility inside and out. It was really impressive. And so, I mean, early communication is good. I don't know how standardized the timing is in terms of like when these initial studies get released and they're, prepared by consultants is just a normal part of the process. But they usually have that. And then we saw people in opposition to this Altair facility, they were citing EJ Screen, like they're using all these same tools that we're using in our project. Like community members are also accessing this. And so they can see kind of what their pre-existing burdens are and where they fall relative to, other populations in the US. But it seems like that sort of like in-person engagement as a supplement to just releasing kind of reports and data can be really really important, and kind of doing it on their terms, and again, like the right multiple languages sometimes, that kind of thing.
Yeah, good points. Thank you. there's been quite a bit of chat in the, and there was a question about kind of plastics recycling. I put in a little bit of data that NREL put together a few years ago, but do you want to comment on, I don't know if you have any data from what you were showing, Corinne, about like recycling rates. And I think John's question is kind of going towards communities that might have like curbside sorting or more, as opposed to like single stream recycling, like what the rates of recycling are for those communities versus maybe communities that everything goes into, one blue bin.
Oh yeah, like are the recycling rates higher in places where they have better source separation? Yes, that did seem to be the case, and that largely tracks with like population density. Like it's just more practical to do higher levels of source separation in like densely populated cities, whereas like in rural places, I mean, sometimes there isn't even curbside recycling, right? Like you load your trash into your truck and you drive it to the landfill yourself. So yeah, I mean, but it's still, because they're only pulling out ones and twos, and so the amount of stuff that ends up in those 3 to 7 bales, it's still most of it. You have a higher percentage, but it's not like 30%. It's still like 10% gets recycled.
Is there data
That,
like, for instance, I live in Champaign, Illinois, and we have recycling bins for the plastic bags that you get at grocery stores everywhere. You go and put them in, and yet there's chatter on the local social media like, well, I work at this store and I just take them out and put them in the dumpster because we've not found anybody to take them. Or it costs us extra and so we don't do it. Or it costs us extra and we do it at this store, but not at this store. And I just wonder what numbers that are there, and maybe ways that we could modify or optimize separation so that we can improve that number.
the data, it leaves a lot to be desired. The EPA does a heroic job of like trying to put this together. They have to rely on waste audits and stuff. That we've also, some of the data that you saw in my talk is from like self-reported data from MRF. So there's like a private company that does these, Government Accountability Associates, I think GAA, that does a MRF survey. But it's not perfect. And we know from looking at that data that like some MRFs are better about filling out all the fields than others. And so it's not 100% reliable. I think we're missing a lot of these like specialty, like if there's a separate facility that's collecting bags, like tends not to be in there. So it's hard to say. I also think there's, some of these companies are happy to take extra money to claim that they are, handling the waste more responsibly than they really are. Like when you pay to just take as much like sort of mass of waste in as you can, if it costs them more to do the right thing, I mean, their companies have gotten in trouble for landfilling stuff when they're getting paid extra to not do that.
Yeah, that's a very like interesting trade-off, and a wholly different dynamic for sure. But which speaks to some other bigger macroeconomic challenges that we're facing. So we are at time. 2.5 hours went pretty quick. I'm kind of amazed by that. But I first want to thank our speakers. Thank you, Corinne, John, Xavi, Ulysses, and Tatiana, for sharing with us your data, your research, what you're working on. I hope that some of the participants reach out and connect about potential collaboration opportunities. I want to thank my fellow organizer, Finola, for helping me organize this and putting together the survey. Please, if you haven't already, go ahead and fill that out. We will just, we'll be using that. And again, I think it'll be very interesting to compare the prioritization of indicators here versus Europe versus the workshop we did in Durban, South Africa. So please, hopefully it doesn't take you too long, longer than 5 or 10 minutes. And then lastly, I want to thank everybody for attending and participating and asking questions. It's great to have many different countries and continents represented here today. from Nepal to Colombia and elsewhere. So thanks everybody for jumping in, whatever time zone you're in. And look out for future IEA workshops. We're going to have another one coming up in October, hosted in Ireland. So with that, we will adjourn. These slides will be scrubbed, but they'll be available on our website. So participants will get access to those once those are available if you want links or references to look at. So thanks everybody, and I hope you have a great rest of your day. Take care.
I filled out that survey about a dozen times now. Is that enough?
That's perfect. Thanks very much, everyone.
Okay.
We've
thanks.
lost our statistical integrity because of you, John. So,
Thank you. Bye.
Thanks.
Okay.
Bye, everyone.
take care.
Thank you.
Yeah.